So today we are going to do chapter 5.7 on page 176. So first let's look at the book. Let's see, maybe like this. We already scanned this page, so, but I'm gonna, being that most of it is new, I will redo it quickly. All right, that should do it. Next page, 178 and 179. Okay, and then a little closer on top and a little closer on the bottom. Okay, that should do it. And finally, page 180 and 81. And this is the end of the chapter, which is very exciting. It's always great to get to the end. Okay, I'll just zoom in on this part. Should be good enough. Yeah, I guess I'll zoom in over here just for the principle of it. Okay, so that's that. So let's look at the bottom of page 176, where we have a subdivision triangle. Okay, remember that a subdivision is a bunch of points that divide up the segment from A to B. So the subdivision is the collection of xk's. So, and they are called a triangle or delta. Then we have, for the subdivision, we have something defined as sigma delta. Now, in case you don't remember what that is, let me show it to you again. It is on page 151. So what we have here is that the delta is the bunch of xk's, okay? Sigma delta is the sum of f psi k alpha xk minus alpha xk minus 1. It's the entire sum is called sigma delta, and the sigma stands for sum. All right, so that is the definition of that. And this has to do with the integral, but we'll worry about that a little later. Now, if we have, being that we have sigma, now we're going to define something else. That's called S delta, big S delta, and small s delta. Now, in the meantime, our f is continuous, and alpha points up like it normally does. So we define big Mk as the maximum within the xk to xk plus 1 range of f of x. Similarly, small mk is the minimum of that little bit from xk to xk plus 1 of f of x. So then big S delta will be defined as the maximum times, so it's very similar to the function f is defined, okay? Except that we have now, so is instead of f of psi right here, we have big M right there. Otherwise, everything's all the same. We have the sum and everything. Now, what that means is this value, by replacing the big M, okay, we have, in the past, we have f psi. F of psi is anything between k and xk minus 1. So f of psi is just some random result in there. Now we're going to replace f of psi k with the maximum of f within the xk to xk minus 1 range. So as a result, that's going to be slightly bigger, okay? And we will define that as big S. Similarly, then small s is defined as the minimum of f. So instead of f right here, where it normally goes, we replace it with a small m, which is the minimum of value of f in that little range from xk minus 1 to xk. And so that we call that the small s of delta. So as you can see, the sigma delta should be between big S and small s. And in the meantime, small s delta is going to be less than or equal to big S delta because the definition that defined as the minimum of f and maximum of f on the same little interval, okay, for each value of k. All right, so that is so basically we're establishing some kind of a upper and lower bound for the sigma delta. And so the next concept we're going to see and following, paragraph, the subdivision undergoes refinement if we put in more points. Okay, we don't take away any points, but we put in more points. If we put in more points, then the subdivision have smaller chunks, right? And but other than smaller chunks is in a way the same as the previous subdivision. It's just as each pieces, some of the pieces might be broken into more pieces, but nothing is taken away. You see, except for individual pieces being broken down more, nothing else is different. Some of the pieces might not be more broken, so it stays the same. That sort of thing. So that is called a refinement. And so now let's consider lemma 1.1, which says that big S points down is decreasing or non-increasing, whereas small s points up, that is as increasing or at least non-decreasing under any kind of refinement. Now, suppose we're going to prove this. Suppose that we will do a refinement of the triangle. Okay, remember the triangle is a subdivision. Okay, we have a bunch of points that cut out from A to B. We're going to make a delta, what is that, 1. And delta 1 will be a refinement of the original delta by introducing 1 point, t. We'll just stick 1 point t between some xi minus 1 to xi. Okay, so we'll stick one more point there. So that little chunk now got divided into 2. So your subdivision has more pieces now by 1. Only one more piece because one of the pieces got broken into 2 pieces. All right. Now, if that is the case, we let big Mi and prime and big Mi double prime be the maximum of f of x in the 2 little chunks, okay, that got broken. Now, if that is the case, then neither Mi prime or Mi double prime is going to be bigger than the original Mi, right? Because the original Mi was the biggest one on the entire chunk that is now broken into 2 pieces. And therefore, being that these are not bigger, we have this conclusion, which is the Mi prime plus Mi double prime is going to be less than just Mi, being that Mi is bigger than both the prime things in this equation. And as a result, the summation is also the same. That is, S delta 1, big S delta 1 is less than big S delta, following the original formula of the big S delta. Okay, so when you sum up both sides of the inequality. Okay, so that is one refinement. We only stuck in 1 point. But any refinement that finite ones, that is, can be just done by adding 1 point at a time, right? So then eventually, after you added enough, as many points that you need, then we have proof that big S delta is decreasing, or it points down, at least not increasing, because it's small. Is always less than or equal to the original delta that isn't broken. Okay, the more you break each chunk into smaller pieces, then your new ones are going to be smaller as a result. So we have proof that big S delta points down, and we can prove the small s delta points up in an identical way, except for flipping the inequality signs around. So that's lemma 1.1. Next, let's consider lemma 1.2. Now, suppose we have 2 different subdivisions, okay? They might not have any points in common, or they might have some points in common. We don't care. We have 2 different subdivisions of the interval a and b, but they're both subdivisions. And then we're gonna, if that is the case, then the small s of one of the triangle is less than the big S of the other one. That is, I mean, the small s is already less than the big S of its own subdivision, right? But we're saying right now the small s is also less than the big S of the other subdivision that it has nothing to do with. That is, the small ones are always smaller than the big ones, okay? And to prove that, what we're going to do is we're going to consider another delta subdivision, the third one, delta 3, or triangle 3. Triangle 3 is a surface will be formed by combining all points of triangles 1 and 2. So whatever points in 1 and 2, we'll just pack it all together, and it becomes a new subdivision. And if there's any point that coincide, we'll just consider that one point. Well, yeah, there's nothing else to do with it. So then if that is the case, then triangle 3 is a refinement of triangle 1 and triangle 2, right? It comes from both of them. It's like from both of them, pieces got cut up. So in other words, it contains both their points. That is break points, let's say. So then by lemma 1 then, now we'll apply lemma 1 directly, and which we get, what does lemma 1 say again? Lemma 1 says that somebody's, big S decreasing, small s increasing, all right? So lemma 2, we're gonna, then small s and more refined, okay, is gonna be small s, I can't even read it that way. Okay, small s triangle 2 is going to be less than small s triangle 3 because by lemma 1 it got refined. Okay, when it got refined, small s goes up under refinement. So small s triangle 2 is going to be less than small s triangle 3. The triangle 3 is more refined than triangle 2. Okay, and then small s triangle 3 is less than big S triangle 3. That's because they are the same subdivision. The small one s is always less than the big S. And then big S triangle 3 is less than big S triangle 1 because it is a refinement. And big S, the refinement goes down. So that is how this entire chain of inequality works out. See, you just go by this fact under refinement and this fact. And small s is always bigger than big S under for the same subdivision. So now that we got this, when you look at it, okay, this might be better. Then from here, we get small s triangle 2 is less than or equal to big S triangle 1. So we're done because we fixed this one. That's the same sentence, okay? Because we never said who's triangle 1 and who's triangle 2, which means small s triangle 1 is also less than or equal to big S triangle 2. So, and that's the proof of lemma 1.2. Now, from lemma 1.2, what we have proven is that any small s is going to be less than any big S, regardless of triangle, okay? You can see that from this inequality again. See, if you stick out any kind of random small s triangle, and then you find a big S triangle, small s is always less, every single small s is bounded above by some big S triangle, doesn't matter which one, which means that if it's bounded, then it has a least upper bound, and we will call it S, okay? Right now, we're under the belief that anything that's bound, a collection of stuff, if it's bounded, then it will have a least upper bound. That is, there's a number where it can't get past it, okay? The bound for it. Otherwise, it's not bounded or something. But there's more to it than that, but we'll just go with that. We're gonna, run with that for now, okay? And so any bounded bunch of numbers have a least upper bound. And similarly, big S has a greatest lower bound. So small s is something that, small s has a least upper bound, and big S is a greatest lower bound. And also the upper bound, small s, is still less than or equal to the upper bound of big S, again because of this inequality. Okay, as these things reaches its least upper bound, is still stuck under these things as it go down to its greatest lower bound. So that's how those limits exist. All right, so next, let's consider lemma 1.3 at the bottom of page 177, where if f is continuous on a closed interval, then automatically small s, that is the least upper bound of the small s triangle, is equal to big S, that is the greatest lowest bound of a big S triangle. Now, now to prove this, by theorem 8, that is just the uniform continuity proof, which says that if a function is continuous, then it is uniformly continuous. Then let's let epsilon and delta be the be as defined in definition 9. Let's go for definition 9 again. Okay, definition 9 on page 172 just says that if you have a function that's uniformly continuous, then given any epsilon, there will be a delta such that any points that x that's within delta, then f of x will be will be within epsilon. Okay? And then we also know later from theorem 8 that continuity means uniform continuity on a closed interval. So now that we need to remember what definition 9 says, let's go back to this thing. So we have epsilon and delta established, found. Okay. Then let's triangle be some subdivision, and where such that the magnitude of the triangle, which is the maximum distance between the x's and one of the sections, has to be less than delta. So we have subdivision that have small partitions. All right. So then the first equation we have is calculating or estimating what big S minus small s is. And here's what I have written down. Now to prove that, the book kind of glossed over it, so I want to put in a little more detail, and you can please do this yourself as well, okay? And so that the whole thing makes sense to you. First, we let's consider one of the segments from xk to from xk minus 1 to xk, and then in that little segment, there's an mk in there, right? The biggest, the maximum of f in that little range. Then the mk will be equal to f of some tk, where tk is in that range. That's because the maximum can be achieved by theorem 7 on page 172. Similarly, let small mk equals to f of t prime k, which t prime k is also within that range. I'm missing a prime here. So similarly, t prime k is also within that range, where f achieves the local minimum within that little range. So we have big M and small m. As a result, then big M minus small m is the same as ftk minus ftk prime. And being that tk and tk prime are within delta, then the f is going to be within epsilon by uniform continuity, and therefore big M minus small m of k is less than epsilon. Yeah, well, because tk and tk minus 1 is less than xk and xk minus 1, because they're both in that range, so which it means they're less than delta. So this inequality establishes. As a result, then let's consider big S delta minus small s delta. Okay, and big S delta is big M, right? Small s delta will end up being small m, and then we sum it all up like this. And so sticking in and that will be less than equal to big mk and small mk is less than epsilon, as we had here, which means this number can be replaced by epsilon. So we plug it out. Okay, so then we only have alpha, the difference of alpha in from beginning to end, which end up that sum, if you work on it, is telescopic and end up being just alpha b minus alpha a, because all the middle terms disappeared. So that is the first thing we proved, which says that the sentence right here, that is big S minus small s delta, okay, which is this thing, and end up being less than or equal to epsilon times alpha b minus alpha a. All right, and so the next thing we're going to do is we're going to take this sentence, this part and the end, okay, we don't pay attention to this part. So being that this is less than epsilon, we're going to rewrite this thing by stuffing in minus s minus big S plus big S and minus small s plus small s in here. So this equation stays. And why are we doing that? Is for a good reason. As a result, this thing is still less than epsilon times alpha b minus alpha a. See, because I minus and then plus and then minus plus the same stuff. So nothing's changed. But now I have a new equation though, okay, that we're going to use to our advantage. All right. So next, we have, let's see. Now let's consider this equation that we just made up, see, with a bunch of minus and plus and minus plus in there. That what about it? Now consider this thing right here that I underlined with what color? Green. Does that look green to you? Well, it doesn't matter. So anyway, and so remember, big S delta goes down to S because it's the least upper bound or something, and that's by lemma 1. And well, big S go down, okay, and S is the least upper bound of S delta, and similarly small S delta goes up again by lemma 1, and to a small s, where small s is the greatest lower bound. So small s will go up to small s delta will go up to s. And therefore, small s delta is always less than or equal to just s, which means this term, okay? From here, we get this term to be positive, right? And this term is also positive because we have this thing minus that. So that is also, so these are both positive terms, which means s minus s, we're going back to this equation right here. Now, big S minus small s, we'll take this equation, which is less than that, and we'll toss this piece and that piece both to the other side of the inequality, like this. So then it less than equal to this thing, right? Minus the first one, that's that one, and minus the second one. We're just doing inequalities here. Now, notice that this value is positive, as we said here, and so is this value because of this. So when you minus two positive values, that you can throw it away, and this is still going to be smaller than or equal to just this value right here, because we're doing the smaller than equation. All right, so what does that mean? That means big S minus small s is less than equal to epsilon times some fixed value. You let epsilon go to 0, then we have proven that they are the same thing. Okay, so big S is the same as little s. Now remember, even though there are limits of something. Now, okay, so next. That was lemma 1.3. So next, let's do lemma 1.4. Okay, on the following page, page 178, we have, we're going to prove that if f is continuous on the closed interval, then the small s delta and the big S delta, the limit as delta goes to 0, will be equal to small s or big S. We just said they're the same thing. So the limit will go to those things. To prove it, we have a quick little proof here. We have we reuse what we just did, okay, this equation. That is equation 1 of the previous page, which I have written down, copied down right here. And we use this thing again, where you have a minus s plus and minus plus, and for a good reason. And we're going to use it as a neat trick. And from this equation, we can get that just this part, you can throw the other stuff to the other side, okay? The other stuff is just small s minus small s delta, because we already proved that this is 0 by the previous lemma. Okay, so then we only have this. And then we also showed previously that this value is positive. And we showed it, where'd it go? Right about here. Yes. So this value is positive. So we can just, we're subtracting it, then this is still less than epsilon alpha beta minus alpha a. And similarly, for small s, this part, we'll take this part and throw the other thing to the other side of the inequality. So less than epsilon and minus the big S. Again, big S minus small s is set themselves as 0, so we only have to subtract by this part. And this part is positive, as said here, okay, this row. And so we can just ignore it, and it's still less than is equal to epsilon times this stuff. And as epsilon goes to 0, then we apply the limit, okay? And for both things, small triangle, the difference is, and therefore the limit of small s triangle or the limit of big S triangle will both go to small s or big S. And therefore, and we have proved lemma 1.4. All right, so next we're going to prove theorem 1. What was theorem 1 again? Theorem 1 is the existence of the Stieltjes integral. That is, theorem 1, now we already used it, but we're going to now prove the existence of this integral, which is defined as such on page 151, okay? And this sum is equal to sigma. And remember, sigma is between small s and big S, because sigma is just some number, right? Where small s is the minimum of f, and big S is the maximum of f. So sigma is between those two values for any kind of a subdivision triangle here. So this is a definition, and we're trying to prove that this integral exists. In other words, this limit converges, is what that means. Now, to prove that, we will, let's see. To prove that for any triangle, okay, small s sigma, small s deltas, that is, small s triangle is less than or equal to sigma triangle and less than equal to big S triangle, as I have just shown. Since they both approach the same thing, then it forces the middle thing to approach sigma delta to approach the same thing also. And therefore, we're done proving. Is that so all the lemmas that led to this point and basically did all the proving for us. So this is just the conclusion of all our lemmas. See, big S, so, well, everything just, as delta goes to 0, by lemma 14, big S and small s both, I think I'm missing a triangle here. Let me add it. Yeah, so that is being that sigma s is between the small s triangle and big S triangle, and they both go to the same limit, so which forces the stuff in the middle to go to the same limit as well, which means the integral exists, as the theorem 1 stipulates. So that is that's that. So next, let's consider the Riemann integral on page 178. By theorem A, which is it's now we know that the Riemann integral of a continuous function exists. Now, what was theorem A again? I mean, theorem A again. Theorem A just says what it just said just now. Okay, I will show you right now. Theorem A says if the function is continuous on a closed integral, then the Riemann integral exists. So that's what we have right now. And as now we have proven that as a special case of theorem 1, because the Riemann integral is a kind of the Stieltjes integral. So theorem 1 proves that the Stieltjes integral exists, and therefore the Riemann integral exists as well. All right, but however, we do remember that you don't have to be continuous for the integral to exist. Certain discontinuous functions are integrable. Right? I mean, such as, for example, some kind of thing that has a so-called a jump discontinuity. If your graph gets somewhere and then suddenly jumps up or down somewhere else, but it keeps going continuous, then it's still integrable. It's fine. We just integrate from point A to the jump, and then you continue integrating from the jump to point B and add it up, right? And because being that the integral is actually the area under the curve, so we just add the two things up. Doesn't hurt a thing. However, there are functions that are so discontinuous that they are not even integrable. Now, you will see that in your homework when you do problem 5, okay? So there is now, here's the book that says something interesting. It says there is an elegant criterion. Notice the word elegant, okay, is what I would call cute. But anyway, there is an elegant criterion which distinguishes between the two, the kind of function that is integrable versus the kind who isn't. And we will state it here without proving it. But first, we'll explain something that's called measure, the point sets of measure 0. So let's look at definition 10. We have a set of points on the line, okay, probably infinite set. This set of points is measure 0 What does that mean? That means given any small epsilon, doesn't matter how small, is positive of course, your set of points can be covered by a set of intervals I. Okay, we're doing the covering again. I, and the set of intervals can be counted. So we can list them as I1, I2, I3, okay, and that's it, no more i's. After you count them all, they can go to infinity, but you can't have more than that. So anyway, we have a set of countable intervals, and it goes I1, I2, I3, and each one will have length of epsilon over 2, and then 2 to the power 1, then epsilon over 2 to the power 2, and epsilon over 2 to the power 3, etc. So the epsilon is small, but it's getting smaller fast as the I goes along. Okay, they just get shorter and shorter and shorter by a ton, because it's dividing by half. So if your set of points can all be covered by such intervals, then given any positive epsilon, okay, not just any, you can toss some epsilon on you and you're fine. No, it's any epsilon that your set of points can be covered this way. If that is true, then your set of points is called measure 0. Okay, remember, it's for any positive epsilon. It has to satisfy any and all positive epsilon requirements. That your set of points has to be able to be covered by it, and then your set of points will be called of measure 0. Now, as an example, let's consider the most obvious set. Let's say x0 is 0, okay, and then x of k is 1 over k. So your set of points is like 1/2, and then 1/3, and then 1/4, and so on. So your set of points is a bunch of stuff that's approaching 0. Let's see. Well, my marker looks quite dim. Anyway, so we have, let me change markers. So my set of points is start at 1/2, okay, and then it goes to 1/3, and then it goes to it just keeps going down 1/4 and 1/5 and so on. So my set of points is approaching 0, but they never actually get there. It just and plus I have an infinite set. Okay, you can continue to go down to 1 billionth, 1 trillionth, doesn't matter. So for this set, we can cover each one with some kind of ik. Okay, you just put ik at the center of whatever your epsilon neighborhood is, right? Each one will line up nicely, and then it will be all covered, right? Because my i's are infinite, so I can slap one on each point. Doesn't matter how small the epsilon it has to be. I can still slap one and cover each point, because each one is only a point, and an interval can always cover a point, even if you have a very small interval. Well, now whether these intervals overlap, we don't really care about that right now. Except that in the homework, they're going to ask you when the intervals overlap. So anyway, but we're not supposed to care. Anyway, so let's look at the next page, page 179. Consider example B. And now we're going to consider the set of all points on 0 from, say, a full line segment, okay, from 0 to 1. Now in this case, all the points on this line segment is not of measure 0. The reason we can prove that is because if it were covered by a bunch of IKs where IK satisfy the requirement, the length of epsilon over 2, epsilon over 3, epsilon over 2 to the power 1, to the power 2, to the power 3, etc., then the total length, if you add up all the lengths of the IK, it is no more than epsilon. And let me show you why that is the case. That's the good old geometric series, okay? And see, now if IK, the length is epsilon over 2k, if you add it all up, that will be equal to epsilon times 1/2 plus 1/4. And remember what that equals. 1/2 plus 1/4 plus 1/8, etc. equals to 1. That's from calculus. Okay, calculus what, 1 or something? Whenever you learn infinite series, maybe 2, 1 or 2. Where this is in fact a geometric series with a simple formula that can calculate the sum right away, which is this thing right here. Okay, and if you don't remember the geometric series, please look it up. It's very easy to learn because it's very short. The sum can be calculated right away. So anyway, the point is the sum of all your ik's is no bigger than epsilon because it's being divided by 2 to some power that's increasing every single step. So the whole thing is dying fast. Okay, so that is, let me see. So that's example B. That's right. So the entire thing, and remember ik has to be satisfied with any given epsilon. So if your epsilon is less than this whole length, and say if it's a half, then of course your ik cannot possibly cover from 0 to 1. It's not long enough, even when you put it all together. So next, let's look at theorem C. Now, theorem C is the theorem we just mentioned, okay, where in the previous page, where it used the word elegant. So it says there is an elegant criterion which distinguishes between the integrable functions and non-integrable functions. Now, here it is. If f of x is bounded on the closed interval, then the integral of f of x dx, the Riemann integral, exists if and only if the set of discontinuities is of measure 0. That is, it can be discontinuous, but as long as it isn't discontinuous in too many weird spots, okay? And if the set of discontinuities is of measure 0, then it's okay. Like these points. If it was discontinuous at all these things, 1/2, 1/3, 1/4, etc., then it's okay. We can integrate it. If it's much more than that, then no. So it's an if and only if situation. Means this is the set of discontinuities being measure 0 is both necessary and a sufficient condition. Okay, that is the two conditions occur hand in hand. One does not happen without the other. And so next, let's consider example C. F of x equal the sine of 1 over sine of pi of 1 over x. You know where this is going, right? There's too many fractions and things are going to go nuts. And so what is wrong with this function? Well, if you stare at it for a few moments, then you quickly notice that when x equal to 1 over k at these points, f of x will not be defined because something is dividing by 0. Okay, yeah, something like that. And well, for this function, you say then how is the function defined? We'll just call it 0 in those points to make sure the function is defined. We don't really care. They are just at these points the function cannot be defined by the sign, so we'll just call it 0 or something. Anyway, so we have a function that does that. Okay, now in this case, by theorem C that we just read, then this function, to integrate it from say 0 to 1, the integral exists. And being the theorem C says so, f is bounded. Okay, bounded is a very important requirement. It doesn't take off and go nuts. So, well, it is already going nuts, but at least it doesn't take off, go nuts locally. So f is bounded, and being that it's a sine, right? Sines are all bounded, and no matter what happens inside the sine, and its discontinuities happens to be the points, this exact thing. Okay, that's why this thing is integrable. Now, I plotted this thing to show you there's no real need for you to look at it. I just thought it would be fun. Here's the graph of sine of whatever this example says. As you can see, it goes nuts at all these points, at 1/2, 1/3, 1/4, etc. And as you can see, it goes nuts more frequently. And when it goes towards 0, you can't see anything. But even if you can't see anything, you can imagine that this part that's all bunched up looks exactly like this part. Okay, that is, if you magnify this part, it'll look identical to this because it'll do this infinitely. It just gets tighter and tighter so your eyes can't see. But magnifying it will make it look just like this. And so that is that, and yeah, it's let's see. Here's what happens at 1. See, this pattern just keeps going, and then on the negative side, it's the same thing except it got flipped over, just like the sine graph. Sine graph is the same thing on both sides, except that what's up becomes down on the negative side. Otherwise, it's the same. It looks the same. So that is our graph. I just thought that was kind of nice to look at, and but there's no real need for you to plot it yourself, I don't think. So now let's look at the homework problems. So for homework on page 179, please do problems 1, 2, 4, 5, 6, 7, 8, 9. And unfortunately, the answer in the book is wrong for problem 9. The problem 9 already gave you the answer. It says to tell you to prove epsilon is less than something, and the book's answer is wrong in a very obvious way. I'm not even sure. Well, I think the reason the book is wrong is because the problem is is of no concern to anyone. Okay, so the author didn't pay that much attention to it, and as a result, he actually made a mistake. Until now, I have never found the book to have made a mistake yet, right? So, so this is startling to me. But I guess it's unfortunate. I was really hoping that we can get through the whole book without finding a single mistake. That would be good. Because the mistakes in the book, it requires more work from me because I have to go through a lot of trouble to make absolutely sure that the book is wrong. Okay, it's not just because, oh, I can't get the answer in the back of the book and therefore it must be wrong. That, you know, that doesn't make any sense. So so anyway, so please go do the homework, okay, bearing in mind that I believe the problem 9 is wrong, and then you can, and then when you're done, we'll talk about them. So next, let's look at problem 1 on page 179. We're supposed to compute S a triangle directly, as if given some specific F and A and B and alpha and all that stuff. And yeah, okay, so let's do that. And basically that means we're going to work with limits or something. Okay, that is just some work that has to be done. All right, so here is what I have. The S is, let's see, we start out by the definition where mk is, we'll use mk as the maximum of f, right? And then copy it in as it says. Here's our subdivision, and with m equals to 2 to the power n. Now, to make this clearer to myself, I created a sample here. You don't have to create a sample. This is just so that I can see it better. Now, a sample would be, I chose n equal to 2, which makes m equal to 4. And yeah, there is not much going on here. I have a picture drawn there, so my subdivision is very small, right? I only divide it into 4 chunks, and as a result, my S triangle then equals to just 2 numbers added together because it's doubled on both sides, so there's a 2 multiplied in front. So that serves as a sample for me to create the general formula. Here's the general formula, which just means it will be 2 times cosine of a bunch of stuff, okay, starting at 0, adding up all the way to m over 2 minus 1. That is, that's in the counting, okay, eventually you get up to that number. Now so which I'll call m minus 2 minus 1 big N just to make the writing easier. So I have this formula. And at this point, the book is very considerate and even gave us a formula for how to sum up these cosines. And so the book's formula says this, right? And which is fine, except that I didn't notice that this number here is 1/2. So at first I couldn't get the answer to come out. This is only 1/2. This is not 1. And I need it to be 1, so I need to add 1/2 to the side. So a little bit of detail that I missed. So I was spinning my wheels at first and couldn't understand why I couldn't get the right answer. Anyway, but eventually I came to my senses, right? The actual cosine formula, if you write it this way, counting from k equal to 0, which means is 1, is equal to the formula the book gave plus 1/2. Don't forget that, okay? So now that I knew this, then everything can be plugged in the formula much better. Let x equal to pi over m, then and let's plug, yeah, and then n equals to m over 2 minus 1, and plug the whole thing in, and we'll end up with this thing right here, which cleans up to look something like this, and where m is, again, 2 to the power n. Now, this thing doesn't really look much like the book answer, which is this thing, or is in the 2 to the minus n form, okay? But when I plotted both graphs on the calculator, I got them to be identical. They're the same graph, which means then this answer is correct. And the reason they look different is because of trigonometric identities or something that we can prove that one equals to the other, which I did right here. Okay, and the rest of it, I did prove that these two formulas are indeed the same. They are trigonometric something identities or whatever. If you look through down here, it isn't actually that hard to get from there to here. Okay, a few steps, and then we got from this basic principle, then we can get that they are indeed the same thing. And of course, the book's formula is better than mine, because mine's more complicated looking, and whereas the book's formula is so much cleaner and neater. And this is the actual formula where m is equal to 2 to the power minus n. And that's the end of problem 1. So next, let's look at problem 2, where what does it say? Let me see. Problem 2 says in exercise 1, let's calculate what happens when we let something go to infinity. Okay, in other words, calculate the limit of S triangle. All right, so for problem 2, I used the book's answer because it's so much shorter and cleaner than the one I came up with. And so let's use it. So using the book's answer, I let thing n go to infinity, and the book answer says 1 plus cotangent, right? We can ignore the 1 because we're dividing by 2n, so that's going to be gone. But how do we do this? This limit isn't obvious to me at first how to calculate it, but eventually if you stare at it long enough, then you realize that we can do a substitution. That is, let u equal to pi over x. Then it becomes, the limit turns into that limit where u goes to 0 because x is going to infinity. Then we can apply L'Hopital's rule, and which gets us here, where the limit is equal to x over sine of x, okay, format. That is equal to 1, as you remember from calculus 1. And being that that's equal to 1, then the whole limit ends up being just 2, which is the integral from negative pi over 2 to pi over 2 of cosine x. And that's what we've been doing this whole time, okay? All this spinning around just to calculate the integral of pi of cosine x. But that is at the end of problem 2. Next, let's talk about problem 4, which states that if we, let's see, what does it say? It states that if, let epsilon and delta be as the proof that we've been using, that is for the uniform continuity, and then such that if x is within delta, then f of x will be within epsilon. Now, if triangle 1 and triangle 2 are two subdivisions of A to B, okay, and they're both within delta, so then their f's will be within epsilon. All right, so show that the difference, the magnitude of their difference is less than 2 epsilon times alpha b minus alpha a. Okay, so let's do that. Here is what I have. Now we have f is uniformly continuous, so as long as x1 and x2 are within delta, f of x1 and x2 will be within epsilon. Now we'll let triangle 1 be a collection of xk, okay, k going from 1 to n. Triangle 2 will be named something else, xj, where j goes from 1 to m. And then we know that the magnitude of triangle 1 will be less than delta, and so is magnitude of triangle 2. Now, and then sigma triangle 1 by definition will be this thing, okay, where it has a psi k, and that is psi k will be some number between xk and xk minus 1. And then sigma delta triangle 2 is similar, will be f, what is that thing called, eta j. So I'm indexing it differently. Well, following this, I guess. All right. So then the difference then, of course, is equal to those two things subtracted. But but they have different indexes, okay? And the xk's and the xj's are also possibly different. So how do we get them to meet as some kind of middle ground? So we're going to do the same trick as it was done in, I think, lemma 1.2, which is that we're going to combine these two subdivisions and then make them a new subdivision called, let's call it delta, in the sense that delta contains all the points from both subdivisions, okay? So delta potentially got cut up a lot more, broken down more. But other than that, however, delta isn't missing any points from the other subdivision. And therefore, delta is a refinement of delta 1 and delta 2. Okay, so now knowing that, then delta is, we'll call it I goes from 1 to n plus n or something. It doesn't matter where it goes. The point is it connects all of them. And of course, some of the points might coincide, and that's okay. Okay, we'll just combine it as one point. Anyway, so after we do that, then we have sigma delta, which is, what is that, eta, this is zeta or something? Well, whatever. I was forced to pick another thing in here to do another variable, Greek variable, to do sigma delta. Now, if that is the case, and then now let's look at this subtraction, okay? Delta 1 minus delta 2. First, it equals to this stuff up here. We'll just minus sigma delta plus sigma delta in here for no reason, except that this is still equal because I'm minusing and subtracting the same thing. And then use the triangular inequality, I got this part down. So now I have these two things to think of. Okay, sigma delta 1 minus sigma delta. And what might they be? So that is going to be equal to that, of course, but I still have a problem of the points might be different, right? Even though all the points in here are included in the points in here, but still, what do you do here? Then we're going to re-index f psi of k. Okay, that is f psi of k used to be, let's say we have xk goes from, here's xk minus 1, k minus 1, and that this is xk, and it might be, and then in here we have f of psi. Okay, we choose psi k as the value to represent this everything in here. So if it gets cut up into 2 pieces or more, doesn't matter, then we will now re-index it as this new x, let's say call it x prime, but the f psi will still represent both values in the equation, and which will change nothing. Okay, then we just add it from here to here, and then from here to here in the summation. So we can do that, being that we have only a finite number of stuff being added. So things are just broken up, and each f, wherever it used to belong to, it will be the same f. So as a result, f of psi will be re-indexed. Okay, we'll call it f psi I instead, and now it will go from I to n plus m. But remember, f psi I, this might be f psi I. I will write it down. So this part might be psi. We'll call it f psi I, okay, psi I, and then this part might be called f psi I plus 1, but they're the same thing. They're both f psi k, okay, because we just have that represent both, so that it's more broken down, but nothing's different. So then in that case, then our re-indexing will keep everything the same, but it will now look like the other one. See, then f psi I is the same as f psi f eta I, or whatever that thing is called. Is it eta? Nah, whatever. The point is, right. So then now everything is lined up. The alphas are going from xi to xi minus 1. See, because now they are called smaller things, but everything is represented the same way. And as a result, this equation is the same as the one above, where we have this one. Okay, so these two are the same equations, but at this point, however, we can now factor out the f psi I minus f eta or zeta. Why can't I remember this thing? Whatever. So now we can factor them out because they're being multiplied by the same alpha xi minus alpha xi minus 1. Now, and being that we have that delta and epsilon definition, being that these things are now within the range, okay, and being the deltas all, the triangles are all less than delta in magnitude, then f has to be less than epsilon. So we can factor out the epsilon right here. And now the sum is just the rest of it, which end up being epsilon times alpha b minus alpha a. And that's just one of them, okay? We had 2 of these things. We have this one and that one. And they're the same. So if one of them is, we can prove one of them satisfy this situation, so does the other one. And therefore, them together will be, as we have here, okay, equal to these 2 things added together. So then the thing we're trying to prove is right here, okay, is going to be less than 2 epsilon times alpha b minus alpha a. And that is the end of problem 4. I will finish the rest of the section in the next video.